Today we are going to be looking at pattern creation, and for that we are going to use the PCAD 2006 pattern editor. We are going to create the TO220 footprint, which we are going to then afterwards link on the LM317 regulator that I've created as part of the symbol editor exercise. Just a brief bit of information on the pattern editor. Similar interface than the symbol editor, where we have place pad. We're going to use that. Place via. In this specific footprint we're not using that. Remember, vias are not to be soldered on. Vias are only there to take a connection from one layer to another layer. It may be from layer 1 to layer 2, or from the top layer to the bottom layer, or anywhere in between. So that is what vias are used for. We are not using it in this specific instance. Here's a place line, place arc, place polygon, place reference point, glue points. In terms of glue points, I just want to mention that glue points are typically not used anymore. It used to be used in wave solder, where you would stick the component down with a little drop of glue, and as the board then goes through the wave solder, the components won't fall off into the solder pot below. We are going to use the place pick point, and we are not going to use the test points. We are not going to define keepouts at this point in time. Place cutout we're not going to use for now. Place text we might use, and place attributes we are definitely going to be using. Again, similar interface as in symbol editor, where we have our ruler here at the top. We have a validate pattern here. So let's get started on the pattern that we want to create. Now, as you can see from the data sheet here, there's a bit of maths that we need to do prior to actually calculating or placing the pads down. What we do need is that we need to get the width of the hole that we are going to be using. As you can see from this data sheet, we are sitting with a pin width of ranging between 0.71 for the minimum pin width to a 0.91 for the maximum pin width. If we basically take the 0.91, we subtract the 0.71 from that, we get a value. We divide that by 2, and we add that to the smallest value, the 0.71, and then we get a pin width that we are going to be using. Then we do the same for the thickness, where we say we have a minimum pin width of 0.46, a maximum pin width of 0.61, and again subtract the 2 from each other, divide it by 2, add it to the minimum value, and that gives us the thickness, the nominal thickness of the pin. So we have the nominal width of the pin, we have the nominal thickness of the pin. Then we use Pythagoras, and we basically get this, where we have 0.9 for our nominal width and 0.47 for our thickness of our pin. We then take the diagonal of that gives us the biggest distance, and we get to a figure of 1.015. Now, typically in IPC, they will have a rule where they say the hole size needs to be at least 0.2 millimeters bigger than the maximum pin width. Now, in this case it's 1 millimeter, so we should have at least a hole diameter of 1.2. But from previous history, I've learned that if you make that at least like 1.3, then we can easily insert the component into the footprint. So I'm gonna not just make it 1.2, I'm gonna make it 1.3. Okay, so let's get going on this. Second thing we need to know is we need to know the pitch between these components. Now, typical through-hole components comes from the 1960s and 1970s, where components were originally created on a 100 mm pitch or a 2.54 millimeter pitch. Modern components are not created in mils anymore, except in the States, where they will still be stuck on working in inches. The rest of the world is working millimeters, so you will find that through-hole components tends to go to inches, hence mils, or and then surface mount components will primarily go on the millimeter unit scale. So based on that, we are expecting to see mils here. Now, typically from this data sheet, you can see that they give you both values. The smaller value that you see here in front is the inch value. If we want to convert inch to mils, we times it by 1,000. So 0.142 inch or 142 mils. And that equates to 3.6 millimeters. So whenever you see a data sheet, you will find usually, if you scroll up, they should give you a clear indication. Let's just quickly have a look. Here they say all linear dimensions are in millimeters, and then between brackets inches. So this is for your surface mount components. Let's quickly have a look at the through-hole component. We should see exactly the opposite in terms of that. So all dimensions are in inches, millimeters between brackets. So that supports exactly what I said, that most surface mount components are created on a millimeter pitch, and all through-hole components are generally created on a mil pitch. So whatever we see the smallest number, that is the number that is in inches. Between brackets, we see the millimeters. So just have a look at the bottom of each document. You will always find that. Okay, so from that, we can see here that we are sitting with a 0.1 inch pitch or a 2.54, or we can say it's a 100 mil pitch. So we know that these pads need to be 2.54. Now, I said to you guys that in symbol editor we work in mils, because our schematic we draw in mils on a 100 mil grid. In PCB footprint, I would suggest we stick with millimeters. So you need to make sure options configure that you are in millimeters, and here at the bottom you can see 2.54. So that's the 100 mil grid that I was talking about. So we're going to use that to place the 3 pads, and then we can actually do the rest of the outline in a 0.05 millimeter grid. So let's get going. We need to first configure the pad. So we go options, pad styles. Now we copy the default pad style. Now we give it a name. My convention, and you don't need to follow my convention, is just if you choose a proper convention and you always stick to it, you can always reuse. And I'm very much for reusability of your symbols and your patterns and your footprints, because I don't like creating the same thing over and over again. So let's create a standard where we can reuse as we're going along. So we're going to start off by saying it's TH. TH for through hole. Surface mount will be SM, followed by colon, then followed by what the pad is. So in this case we are going to basically make a round rectangular pad. So we're going to go RR, round rectangular, followed by the dimensions X for the X axis and the Y axis. Now if we look at this pad with this calculation again, we saw that we need a pad of at least 1.2, so I said 1.3. Now the general rule to start off with on a pad dimension is to say whatever the diameter of the pad is, times it by 2. That gives a good pad diameter for the pad. Okay, so for a hole size of 1.2, we need a pad diameter of 2.4. For a pad diameter or a hole diameter of 1.3, we need a pad diameter of 2.6. Now, I know for a fact that 2.6 is going to be too big for a TO220, so I'm going to slightly break my rule and say 2.4 by 2.4, so x and y 2.4, underscore d 1.3. So the underscore d, the d stands for diameter. So as you can see, my naming convention, it's very clear that it's a through-hole pad, it's round rectangular, it's got an x and y of 2.4, it's got a diameter of 1.3. So we click OK. We then click on the pad, modify simple. Here we say 2.4. Here we make it 1.3, and we choose round rectangular. The rest you can leave as it is for now. That's right. Okay. Now let's double click on this pad to make it current. Wherever you see the asterisk, that's the default pad it will place when you go place pad here at the top. So we need to make it the current one, so we just double click on it. It makes it active now. So let's go place pad. It starts off with pad 1. We click OK. You can choose any way to start, but obviously you would have to zoom in. There you go. There's my first pad, there's my second pad, and my third pad. I am on a 2.54mm grid, so every dot is 2.54mm. And from the data sheet, we know that it should be 2.54. Okay. So there we go. At this point in time, S to deselect. Now, just a comment on the spacing that we see here between the pads. That spacing between the pads are very small. You're going to probably get solder bridges, so there I want to basically reduce the pad size ever so slightly. So we go modify simple, and we make this 2mm. So we only make the width 2mm. I just want to basically go and make this grid 0.05 at this point in time so that I can nicely measure it. So let's go and quickly measure between this point and this point, and we see here from the bottom we have a clearance of 0.5 millimeters. 0.5 millimeters is acceptable for normal hand soldering, so we can use that. We also need to watch out that we don't reduce this pad too much. Currently it's 0.35. Now, as I said to you guys, most manufacturers in the world can do an annular ring of 0.2 millimeters. So this 0.35 millimeters meets the requirements of most fabricators in the world. So let's stay with this pad. We don't want to reduce it further. We have a good distance between the pads to facilitate good soldering. We have met the annular requirement in terms of fabricating the board, so I think we are good to go on these pads. We've placed them on a 2.54mm grid. The next thing we need to do is we need to determine the width. So from the width you can see minimum width with thickness of the components 4.25, 4.65, and we have a width of 9.65 and 10.65. So from that we can say, okay, let's define our outline. Now our outline is very critical because, as you know, I said to you guys, you need to place the silk screen of the components at least 0.5 millimeters from each other. That facilitates good soldering, and it gives you good clearance around your component as well. So for that we're going to use the maximum material condition, in other words the maximum dimension that we see here. So we're going to define a block 10.67 by 4.65. Now just a note on this 10.67, that's a really odd value of working with. Now I typically work on a 0.05 millimeter grid, so I wouldn't go anything smaller than that. So I'm going to just round this down to 10.65 to facilitate my drawing of my block. Next we're going to go place line, and here we need to at the bottom say on which layer it is, so we're going to draw it on top silk. Here we're going to say the line width 0.2 millimeters, most fabricators can manufacture. So at this point in time, let's go and place the line. So we place the line, and if you draw your line and you see this, and you can press O again. So here we keep on watching here at the bottom the dx, and we get that to 10.67 millimeters, 10.65. There we go, there's 10.65. Then I just click and I let go. Then I press backspace to just take this little horrible little segment away. Then I click again, and now I do the bottom side going to 4.65, like that. Backspace again, click again, zoom in, zoom out with plus and minus. Oops. There we go. Right click. Okay, there's my box defined. Now I'm going to draw a diagonal line. So I press O again to give me free angle, and I'm going to just draw this. The reason why I do this is I want to determine the middle of that line. So that's the only reason why I'm doing it. I'm not going to place this box in the center, because if you look here, the pads are not sitting in the center. They give you a distance here, and that's what you need to use. Now have a look. You first need to determine the nominal distance. So again, you take the 0.61, you subtract the 0.46 from it, you divide it by 2, you add it to the 0.46. Then you get a distance of 0.405. So that is the distance that you are going to be working with. Then you also need to take the 2.03 minus the 2.92, divide that by 2, add it to the 2.03, you get 2.69. So you take that nominal distance plus half of that thickness, and that gives you then a distance of 2.89 millimeters that we need to be from the edge to the center of this pin. So we are going to be working on 2.89. Now, in order to get that line going, I'm just going to draw a help line for now that we are going to be extending upwards. Again, 2.89 is a bit cumbersome, so we just make it 2.9 for now. So there we have the 2.9 millimeters. So that's the distance from the back side to the center of this pin. That is that line that I've drawn there. So we select this block, we go to the center. I'm going to just make my grid slightly smaller, because otherwise I'm going to run into issues. And then I go down to the middle of the line. I can press X to cycle through my cursor styles. I grab it. So there I've got it on the center line. I can press Q to go to draft mode. I go down and I put it right there in the middle. So as you can see, the cross is not in the middle. It doesn't need to be in the middle. The distance from the back side to the center of the pad needs to be the 2.89. So now I can delete these help lines as well as that help line. Press Q again to go outside of draft mode. Now the only other thing we want to do is we want to put this little tab in as well. Now as you can see, the tab maximum width, maximum material condition is 0.61. So again, I'll work on 0.6. So I go back to a 0.05 millimeter grid. I choose place polygon. I get it down on there, and I go 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and I draw my block inside like that. Okay, so there you go. There I've drawn the outline, and I've drawn this tab. So now my orientation is correct. Next thing I need to do is I need to place a reference point. So the reference point I always place in the center of the component. So that needs to go here. But as you can see, my grid's not right. So let's just set my grid to 2.54, and then we can go and place the snap point, and then I go back to 0.05 millimeters again. Okay, so I've got my grid point down. Let's quickly see what do we still need. Validate pattern. It's missing a reference designator. So we go place attributes, component, revdes, and again we need to define a text style. So I go to text style, I say add text style. I can use the default one as a starting point, and I will call it revdes. We make this revdes 1 millimeter or 1.5 millimeters tall, again with a 0.2 millimeter width. We go OK. We can verify 1.5, 0.2. That's done. Double click on it to make it current, and we place it center, and we can tick this right side reading. That means when you turn the component, it will always be correctly orientated, reading left to right. So both horizontal and vertical orientation, you don't ever need to worry about checking that your designators are maybe the other way around. So tick that. So we've got the revdes, we've got component revdes style. Boom, there we go. We drop it down. Okay, so we've got the revdes. Let's quickly validate. It wants to have a type as well. Now the type we are going to place down because that makes PCAD happy, but we are not using that on a board. So we place attribute again, component, type. We select revdes, that's fine. We make it center. Don't worry about right side reading, we're anyway going to hide this. Place it down. Now what we need to do is we need to click on it, right click, properties. We make it invisible, so you need to click on it twice. There it is. Then we drag it inside the component. The reason why is if you don't drag it inside the component and you are busy on your PC board and you accidentally click here, you might actually select an invisible piece of text. So I just drag it to the inside of the component always, then I can never accidentally click on it. Next thing we need to do is for the assembly drawing, we need to basically copy this outline as well, because somebody needs to assemble this board for you, and the way you get the person to assemble it correctly is by giving them an assembly drawing. Now that's a separate layer. You guys haven't dealt with this yet, but I'm going to quickly show you how to do this. So first of all, we need to copy everything that's on our silk screen layer like that. So we go copy and we go paste like that. We drop it on top of the outline. While it's still selected, we choose from the layer, we choose top assembly. We then go edit, move to layer, and that's it. So now we've moved everything that we've selected to that layer. Next thing we need to do is we need to create another attribute, component, revdes. We now call it revdes2. That is basically the reference designator text that we'll be using for the assembly drawing. Again, we go to text styles, add. I can use that as a starting point, or I can say let's use default as the starting point. We call it revdes2, and we define it as a true type 1.5 millimeter. Why that? That is just what I'm using. You guys can use anything you want, but for me that works very well. So make it true type 1.5, and that is set now for revdes2. So let's just select revdes2 as that, make it center, again right side reading. We need to make sure that we're on the top assembly drawing, and then it's a matter of dropping that into place, and there you go. So now we've defined the assembly drawing, it's sitting there. We have defined the designator, we've put the type in, so technically when we compile, no errors. So at this point in time you have created a 20220 perfectly. It's ready to be saved and used for future projects. Let's save it, file, save as. again, we save it in your library that you've created. So I'm just going to quickly get to there. My library, I'm going to save it in my library, and we are going to call it TO220. And then I need to distinguish or differentiate between horizontal and vertical, because this is the vertical one. The component stands upright. As you can see here, the component is drawn from the top view. Now the way this component is inserted is vertical, perpendicular to the board. So this is a vertical component, so we specify it as vertical. We have specified the library, so we click OK. So now we have created a through-hole component using the manual way. Again, you can use the wizard as well, but before you use the wizard, you need to make sure that you have created the correct pads. So first of all, when you start up like this, you need to go to Options, Pad Styles, create all the pad styles that you are going to be using in the wizard. That's the first and foremost thing that you need to do. Once you have created the pad, then only you run the wizard. So you go to Pattern, Pattern Wizard. Here you can specify what are you creating. So we are going to basically create a dip. It's technically not a dip, but it's a good way of working this whole thing. We're gonna say, okay, pads downwards and pads across. So pads across is in the X direction, pads down is in the vertical direction. So obviously, to make it to 20, it's a bit of a hack, so this is why I personally like creating the component manually, especially for a 220. PCAD has a very limited amount of components that it can create. It can create dip packages, it can create quad packages, meaning pads on 4 sides, and it can create an array like a BGA. So we can use this, and I'm going to quickly show you how to do this. So pads down, we choose 3. Pad spacing on, 3. I should actually just type in 3. Pad numbers across, we want to actually have that at 0. Pad to pad spacing on center, we want to have 2.54. And the pattern width, we don't worry too much about that at this point in time. And here we select the pad style, so we choose that pad style, and as you can see, it doesn't work very nicely in terms of creating that. You need to, because it's a dip package, you actually need to have 6 pads, and then we're going to take 3 away, so it's a bit of a workaround, unfortunately. And also you can see that I went and rotated the 1 pad. They should all be rotated in order to make the correct pattern. Then we can say the box width we can actually specify, so we can make that the silkscreen line width is 0.2. The rectangular width we make 10.65. The height we make the thickness of the component, which is 4.65, and we don't add a notch at this point in time. As you can see, the orientation is wrong, so let's just cut that and paste that there. It doesn't work. 10.65, 4.65. There you go. So as you can see, I went and created that box there now. The notch, we're not going to have that on here. Again, we're not creating an IC, we're creating a 220. So as you can see, it's a bit of a workaround. You can go finish. There it went and created the reference designator and the box and everything, but you still need to drag this box over there. You need to basically strip these pads away. You need to name these pads. So I'm not going to carry on further with this. There's some surface mount examples where I can more effectively show you the working of the pattern wizard. I just wanted to show you at least what can be done with pattern wizard, but from this example you can clearly see that the pattern wizard is not always your friend when you create your patterns, and you need to use the pattern wizard only when you can actually benefit from it. Doing it this way just wastes time. So you could have just gone and created this pattern manually by yourself like I did in the beginning. So this basically concludes the whole pattern creation. Again, there's some options you need to make sure. So options, selection mask, make sure that you are touching block. Options, configure, need to make sure that you're in millimeters. And options, preference, mouse, make sure that you control subselect, shift extend selection. You have the double click display properties disabled. That will give you the correct settings. Again, you can alter and change as you want. This is just the settings that I use. Let's just quickly, as a last point, go back to my library, go back to the TO220 that we've created. We have put the reference point in, but we have not given it the glue point and the pick point. So again, the glue point is not necessary for a through-hole component, but the pick point, that is where your pick and place machine will pick it. And yes, a pick and place machine can pick up a through-hole component. So we're going to place the pick point right there on the reference point, and we are going to save it. So we're going to save it, TO220, in that library. OK. Overwrite, yes. So this is how you create a pattern in PCAD Pattern Editor.